Dear students, continuing to our previous lecture on carbanions, where we have discussed the structure, stability, and generation of carbanions. In the present lecture, which is in continuation of our series of lectures on organic reaction mechanism, we will be discussing reactions of carbanions. So carbanions being strong bases, they are also very reactive and unstable in nature, and because of that they undergo a variety of organic reactions. The prominent among those reactions, they are displacement reactions, condensation reactions, elimination reactions, addition reactions, rearrangement reactions, then anionic polymerization, then Yolide reactions, and Amplock. So we will discuss examples of each and every type of reaction which the carbanions undergo one by one. The first is displacement reactions. Now here in these types of reactions, carbanions, they can combine with positive species in a displacement reaction. And most common examples of these types of reactions take place in case of beta keto esters with alkyl halides in the presence of base, or second example is reaction of 1,3-diketones with alkyl halides in presence of base, and third is alkylation of acetylides. So for example, the first one, the beta keto esters, as we have discussed in the last lecture also, that because of the presence of these carbonyl groups, these protons, they become very acidic protons, and because of their acidity they can be easily abstracted by a base. So when beta keto esters, they are reacted with this base, say ethoxide ion, this proton will be abstracted to generate this type of carbanion, and then this carbanion will act as a nucleophile to substitute this bromide on the alkyl halide. So when beta keto esters, they will react with alkyl halide in presence of base, they will be converted into these types of beta keto esters where H will be alkylated. H will be displaced by this alkyl group. So basically this is an alkylation reaction. So carbanions, they will help the organic compounds like beta keto esters to alkylate. So we will get substituted beta keto esters as the product. Similarly, beta diketones, here also because of the presence of these carbon oxygen double bonds, carbonyl group will make these protons very acidic, and again in the presence of the base, this or this proton, they can be abstracted very easily to generate this type of carbanion, and again this carbanion can act as a nucleophile, and this will displace this bromide ion or halide ion from the alkyl. So here again alkylation of beta diketones will take place. H will be displaced by R group. So this type of displacement is called as displacement reaction in case of carbanions. Similarly, in case of carbon-carbon triple bond, if we take the example of acetylene, acetylene in the presence of a very strong base like sodamide, this sodamide will abstract the proton on acetylene because this is acidic in nature because of the presence of carbon-carbon triple bond. We will get acetylide ion, and this carbanion will again displace halide ion from the alkyl halide, and alkylation of the acetylene will take place. So unsubstituted carbon-carbon double bond, they will give us mono-substituted carbon-carbon triple bonded compounds, or unsubstituted alkynes, they will be converted into substituted alkynes. So basically hydrogen H has been replaced by R. Alkylation of the acetylene has taken place. So all these examples, they are the examples of displacement reactions. Then is condensation reactions. In most of the condensation reactions, carbanions, they act as a nucleophile. And the common examples of condensation reactions, aldol condensation, where two molecules of aldehydes or ketones, they condense with each other to give us aldols as the product. Or one molecule of aldehyde can react with one molecule of ketone to give us aldols as the product. So the reaction take place either in the presence of a base. So here again, because of the presence of this carbonyl group, these protons present on the adjacent carbon, they are acidic protons. So the base will abstract any of the proton from the adjacent carbon, and a carbanion will be generated. And this carbanion will act as a nucleophile, and this will attack the uh, electrophilic carbon of the second carbonyl molecule. And like this, these types of products, which are called as aldol products, they are formed. And this reaction is known as aldol condensation. And we can see that in aldol condensation, carbanions, they act as reaction intermediates for formation of aldol products. Similarly, another example is Perkin reaction. So here the aromatic aldehydes in presence of basic medium, they are converted into cinnamic acids. So if we are having this aromatic aldehyde, say benzaldehyde, if aryl is phenyl, then we will get cinnamic acid as the product. So basically what happens is uh, this acetic anhydride will act as a nucleophile, will attack at the aromatic aldehyde, and condensation will lead to the formation of these types of products. And here again the intermediate used is a carbanion. Then third is Dieckmann condensation. So Dieckmann condensation is again the conversion of diesters to beta keto esters through intramolecular reaction. So here what happens is because of the presence of these ester groups, the adjacent protons on these carbons, they are acidic protons, and this base can abstract either this proton from here or proton from here, this being a symmetrical diester. So either carbanion can be generated at this place or at this place, we will get a symmetrical carbanion. So that carbanion then will attack, if suppose carbanion is generated at this carbon, then this carbanion will attack this carbonyl, and OR will be eliminated and cyclization will take place here, and we will get these types of beta keto esters as the product. And this conversion of diesters into beta keto esters through intramolecular reaction in presence of a base proceeds through the formation of carbanions, either at this carbon or at this carbon by a base. And this reaction is known as Dieckmann condensation. Similarly, Claisian condensation is also an example of the reactions where carbanions they act as reaction intermediates. So here either uh, two ester molecules they are converted into beta keto esters, or one ester and one ketone molecule they condense with each other to give us beta diketones as the product, and the reaction is known as collision condensation. And here also what happens is that because of the presence of this ester group, the adjacent carbon atom, this one, this carbon having two hydrogens becomes a acidic hydrogen, and these acidic hydrogens they can be very much abstracted by a base. So sodium alkoxide can be reacted as a base. Then a carbanion will be generated at this place, and this carbanion will attack the carbonyl group of the second ester molecule, and we will get these types of uh, condensation products, that is beta keto esters as the product with the elimination of one molecule of the alcohol. So all these condensation reactions they are examples where carbanions they act as reaction intermediates during the formation of product in all these reactions. The next is elimination reactions. In elimination reaction also, carbanions they act as intermediates. So for example, if we are having this substrate, say 2-phenyl ethyl bromide, and because of the presence of this phenyl group and then electron withdrawing bromo group, this carbon is having delta positive charge, and because of that this will attract electron density towards itself, and this proton or this proton, both are symmetrical protons, they will become acidic protons, and they can be easily removed by a base. So when base is present, say ethoxide ion, this will abstract this proton and a carbanion of this type will be formed, and then this will move to this place to create a carbon carbon double bond, and bromide ion will be eliminated. So this is how 2-phenyl ethyl bromide in the presence of basic medium is converted into styrene as the product, and this is an example of elimination reaction. So many type of such reactions they can take place where carbanions they will act as reaction intermediates. Then is addition to unsaturated compounds. This is also an example of reactions in organic synthesis where carbanions they are involved as intermediate. So for example, if we are having these types of compounds where X and Y both are electron withdrawing groups, and because of this X and Y being electron withdrawing group like cyano, halogen, ketone, carbonyl, and ester group. So if X or Y they may be same or they may be different. Say X is CN, Y may be halogen. X is halogen, Y may be COR, or both may be same, both may be different. But the basic thing is that this X and Y they should be electron withdrawing group. And because of this, these types of compounds where X and Y they are electron withdrawing, this will create a positive charge at this delta positive charge at this carbon due to inductive effect, and these protons they will become acidic proton, and they can be easily removed by the base. So that is why these types of compounds they are called as uh, uh, alpha methylene or active methylene compounds. So active methylene because this methylene group becomes very active because of the presence of electron withdrawing X and Y groups. So in the presence of a base, one proton will be abstracted and we are left with this type of carbon. And now this carbanion will act as a nucleophile, and this can add to unsaturated compound. So unsaturated compound can either be alpha beta unsaturated carbonyl compounds or alpha beta unsaturated nitriles like this. So this will attack at this carbon, this will go to this place, this will go to this place, and then ultimately addition will take place at 1 and 2 position, and these types of products they will be formed. So this is how carbanions they act as nucleophiles and add to the unsaturated compound to give us different types of uh, organic functional group transformation. So when addition takes place to alpha beta unsaturated carbonyl compounds like this, 1,2 addition takes place and the reaction is called as Michael addition or Michael reaction. So alpha beta unsaturated carbonyl compounds on reaction with active methylene compounds, they gave us 1,2 addition products, and reaction is known as Michael addition. Then carbanions, they are also involved in some rearrangement reactions. Also, these are not as general as in case of carbocations. Carbocations, we have seen they undergo a variety of rearrangement reactions. But here there are only few examples of rearrangement reaction in case of carbanions, and this rearrangement takes place due to stability of the carbanion. And for example, if we are having say this substrate, and if we react this substrate with sodium metal, we know that because of the presence of these three phenyl groups, the electron density will be attracted towards this, and this carbanion formed uh, will be a very stable carbanion, and this is a primary carbanion, and with 1,2-phenyl shift this will be converted into a tertiary carbanion, and we know that the tertiary carbanion is much more stable than the primary uh, carbanion, and because of the stability of the carbanion, this rearrangement has taken place, and then this will interact with H ions and we will get this type of product, which is not a normal product but a rearranged product. So normal product would have been if H ion would have attached to this carbon. So here the rearrangement has taken place because of the stability of the carbanion formed by rearrangement reaction. The second example of involvement of carbanions as intermediate is in case of Fibresky rearrangement. So this rearrangement take place in case of alpha haloketones, where the alpha haloketones they are converted into carboxylic acid derivatives due to this Fibresky rearrangement when the reaction is taking place in presence of a base. So and similarly, if we are having open chain alpha haloketones, they will be converted into carboxylic acid derivatives. But if we are having cyclic alpha haloketones, then the Fibresky rearrangement also constitute a ring contraction reaction. So for example, if we are having this 2-chloro cyclohexanone, and we know that because of the presence of this carbonyl, these protons they are acidic protons, and because of that the base will attack this proton and a carbanion of this type will be generated with the removal of H ion from here, and base they will form a water molecule. Then this carbanion will act as a nucleophile and attack this carbon to eliminate this halogen, and we will get a symmetrical cyclopropanone derivative. And we can see over here this 6-membered ring. Now this has become 5-membered and a cyclopropanone ring has been formed. And then that base will again attack at the electrophilic carbon, and then either this bond will break or this bond will break, because this is a symmetrical intermediate. So either this bond break or this bond break, we will get the same type of product. So this is how the 6-membered ring alpha haloketones, they are converted into 5-membered ring carboxylic acids as the products, and ring contraction has taken place. Then another example of involvement of carbanions as intermediates is in case of anionic polymerization. So anionic polymerization of styrene in the presence of sodamide base is the best example of involvement of carbanion intermediate. So here R is electron withdrawing group, and if we say styrene, that means R will be phenyl over here. So when R is phenyl, that means this will attract intensity, electron density towards itself, and this bond will neutralize the positive charge created on this delta positive charge created on this carbon, and that is why this carbon will be an electrophilic carbon, and this will be attacked by the initiator. Z negative is an initiator used for these types of polymerization reaction. So Z will get attached to this carbon and a carbanion of this type will be generated. So monomer carbanion is formed when monomer reacts with the initiator. Then we know in polymerization there are 3 steps: initiation step, propagation step, and termination step. So in the initiation step we will get an intermediate which is a carbanion. Then this carbanion intermediate will react with number of monomer molecules to get converted into macrocarbanion, and then this macrocarbanion will terminate in different ways to give us a saturated polymer as the product. So this can couple with some cation, anion can couple with some cation, and saturated polymer, they they can be formed. So if we will start with styrene, that means the kind of product formed will be polystyrene. So formation of polystyrene from styrene in presence of sodamide base is an example of the reaction, polymerization reaction, where carbanions, they are acting as intermediates. So if sodamide is the base, that means NH2 negative is your Z. Then is Yillid reactions, both sulfur and phosphorus, as I have told you in the last lecture, they act as carbanions. So for example, this phosphorus yellate, which was formed from triphenyl phosphine and methyl halides, they act as phosphorus yelates, or because of the presence of negative charge, this is a carbanion, and then this carbanion can react with aldehydes or ketones, say carbonyl compounds. So basically what will happen, this oxygen will be shifted to phosphorus and this CH2 group will be shifted to this carbonyl group, and we will get alkenes as the product. So carbonyl compounds, they will be converted into alkenes when phosphorus yelates they are used. and this reaction is called as Wittig reaction. Similarly, if we will react sulfur ylides with alpha beta unsaturated ketones, then instead of alkenes, we will get epoxides as the product. So this CH2 will add across this carbon oxygen double bond. Instead of forming alkenes, we will get epoxides as the product. So this is the difference between the products formed by phosphorus ylides and products formed by sulfur ylides when we are reacting these with alpha beta unsaturated ketones. Then is Amplock, and we have seen in the previous lecture that these are the reaction where inversion of polarity take place. For example, in case of alkyl halides, R is the positive part, alkyl is the positive part, and X is the negative part. And if in the next step R becomes negative, and that means polarity of the R has been inversed. So such type of reactions, they are called as Amplock reaction or polarity inversion reaction. And chemistry of dithiene, this is a classic example of polarity inversion or Amplock reactions. So here, as we have seen in the previous lecture, carbonyl compounds, they react with 1,3-dithiols to give us these types of dithienes, and these on reaction with a strong base at minus 40 degrees centigrade will generate these types of dithiene carbanions, and these carbanions can interact with different types of substrates to give us products through polarity inversion. So this will react with epoxides. We will get these types of dithiene intermediates, and these on hydrolysis will give us these types of ketones as the product. Similarly, ketones, they will be converted into alpha hydroxy ketones as the product, and these aryl halides, they will be converted into these types of ketones through Amplock or polarity inversion reaction. So this carbanion will act as a nucleophile, and this will attack, say, this carbon, this bromide will be eliminated, and this type of intermediate will be formed, and then this is hydrolyzed, this will be converted into carbon oxygen double bond, and we will get these types of product. Similarly, in this case, this carbanion will attack this carbon, lactophilic carbon, and this will become OH, this will become this type of intermediate, and when hydrolysis is done, this group is converted into keto group. Here, this hydrolysis H, one H will go to this sulfur, one H will go to this sulfur, and oxygen of the water will get attached to this place, and we will get hydroxyketones as the product. Similarly, in epoxide, this will attack at this position, and we will get these types of intermediate, and then hydrolysis of this will create a ketone group over this place. So this is how polarity inversion reactions will lead to the formation of different types of products through dithiene carbanions. So these are the books which has been used to prepare this reaction, in addition to some internet sources which has also been used for preparing this lecture. Thank you very much.